Good day, class. We'll begin this time one of the most important topics in tropical design. On our previous topic or lesson, we focused primarily on climate, environmental analysis, and passive environmental systems at the building scale. Today, we expand our perspectives. We move beyond the building and begin studying the site itself. A building never exists independently. Every building is influenced by sunlight, wind, vegetation, water systems, landforms, and urban conditions. Collectively, these environmental conditions create the microclimate. One of the biggest mistakes in architecture is attempting to design a building before fully understanding the site. In reality, site planning is often the first and most important environmental design decision. A well designed building on a poorly planned site may still perform poorly. However, a thoughtfully planned site often improves environmental performance before the building is even constructed. This topic teaches us how to use site planning as an environmental design tool. The objective of this module extend beyond simply understanding environmental conditions. As future architects, you must learn how to interpret environmental information and transform it into design decisions. And by the end of this module, you should be capable of evaluating how local site conditions influence building orientation, building placement, landscape planning, environmental comfort, and site sustainability. You should also be capable of proposing passive environmental strategies based on actual site conditions. In professional practice, architects are constantly required to analyze unfamiliar sites. Your ability to read and interpret a site often determines the success of your design. To understand site planning, we must first understand microclimates. A microclimate refers to localized climatic conditions occurring within a specific area. Even within the same city, two sites can experience completely different environmental conditions. Consider these examples: a shaded park, an asphalt parking lot. Both may be located only a few meters apart, yet temperatures can differ significantly. Why? Because local environmental conditions influences heat gain, airflow, humidity, and thermal comfort. Several factors create microclimates like vegetation, water systems, buildings, topography, and surface materials. Microclimates are important because people do not experience regional climate directly. They experience the immediate environmental conditions around them. As architects, we design for microclimates. Many people believe architecture begins with the building. In reality, architecture begins with the site. The site determines opportunities, constraints, environmental performance. So, site planning affects almost every aspect of architectural design. A poorly oriented site increases heat gain. Poor drainage creates flooding. Improper placement may block ventilation. Conversely, intelligent site planning can improve comfort naturally. Good site planning often reduces future energy consumption and increases environmental resilience. Therefore, architects must treat site planning as a fundamental design activity rather than a preliminary step. Before architects begin designing, they must first collect environmental information. This process is known as site analysis. Environmental site analysis identifies how the site behaves environmentally. Key information includes climate factors, sun, wind, rainfall, temperature, humidity. Physical factors, slopes, vegetation, water systems, and existing development. Site analysis transforms assumptions into evidence. Without site analysis, architecture becomes a guesswork. With site analysis, architecture becomes environmentally informed decision making. Site responsive design is a philosophy of environmental respect. Instead of imposing a design upon a site, architects studies the site and allow environmental conditions to guide design decisions. Site responsive architecture respects existing landforms, vegetation, drainage systems, and climate behavior. This approach often includes construction costs, environmental impacts, resource consumption. The site becomes a partner in the design process rather an obstacle to overcome. Building placement is one of the most influential environmental decision architect makes. Even small changes in a building location can significantly affect heat gain, airflow, drainage, views, and comfort. Proper placement allows architects to maximize environmental opportunities while minimizing environmental problems. This is why environmental analysis should occur before finalizing building locations. Topography is one of the most powerful forces shaping architecture. The shape of the land influences water movement, air movement, accessibility, and construction methods. Many architects unnecessarily alter natural landforms. However, working with topography often creates a more sustainable and environmentally responsive solutions. Topography should be viewed as an opportunity rather than a limitation. Vegetation is not decoration. Vegetation is environmental infrastructure. Trees and plants performs environmental functions that directly improve the building performance and human comfort. They provide shade, cooling, air purification, and habitat support. Strategically, integrated vegetation often produces significant environmental benefits with minimal energy input. In tropical architecture, vegetation should be considered an essential design element. Landscape integration is one of the most important or powerful environmental tools available to architects. Unfortunately, landscape is often treated as an afterthought. In reality, landscape should be planned simultaneously with architecture. Landscape affects thermal comfort, airflow, solar exposure, human behavior, and environmental quality. In tropical climates, vegetation functions as a natural cooling system. Trees reduce heat gain through shade while plants cools surrounding air through evapotranspiration. Landscape also improves the quality of outdoor spaces. People naturally prefer comfortable environments. A shaded plaza will attract more users than an exposed concrete area. Landscape, therefore, contributes both environmentally and socially. Good. Tropical architecture integrates buildings and landscapes into one environmental system. Trees are among the most effective climate control devices available for architects. Unlike mechanical systems, trees requires no electricity and provides environmental benefits continuously. Trees cool environments through two mechanisms. First, shade. Second, evapotranspiration or evapotranspiration. Shade prevents solar radiation from reaching surfaces. Evapotranspiration cools surrounding air through moisture release. Research has shown that shaded surfaces may be significantly cooler than exposed surfaces. Trees, strategically positioned around buildings, can substantially reduce cooling loads. This is especially important for west facing facades because afternoon sunlight creates some of the highest heat gains in tropical climates. As architects, we should think of trees not as landscaping accessories, but as environmental infrastructure. Green corridors are increasingly important in sustainable urban design. Rather than creating isolated pockets of vegetation, planners establish continuous landscape networks that connect multiple green spaces. These corridors improves environmental comfort or performance by allowing air movement, ecological connectivity, pedestrian comfort, urban cooling. Green corridors also support biodiversity by creating habitats and migration routes for wildlife. From a microclimatic perspective, green corridors help distribute cooling effects across larger urban areas. Many contemporary sustainable cities are investing heavily in green corridor systems because they provide multiple environmental benefits simultaneously. This demonstrates how landscape planning can operate at both architectural and urban scales. One of the most important environmental challenges facing tropical cities is the urban heat island effect. Urban heat islands occur because cities replace natural landscapes with heat absorbing materials such as concrete, asphalt, glass, and steel. These materials absorbs large amounts of solar radiation during the day and slowly releases heat throughout the evening. So as a result, urban areas remain warmer than surrounding rural environments. This phenomenon increases energy consumption, thermal comfort, air pollution, and heat risks. For tropical cities already experiencing high temperatures, urban heat islands create even greater environmental challenges. Architects must therefore actively participate in heat island mitigation strategies. To solve environmental problems, architects must first understand their causes. Urban heat islands are primarily caused by replacement of natural landscapes with hard surfaces. Vegetation that once cooled environments is removed. Natural soils are replaced by asphalt, concrete, and pavements. Buildings become denser and air circulation decreases. At the same time, vehicles, industrial facilities, and cooling systems generate additional heat. Collectively, these factors create hotter urban environments. Understanding these causes allows architects to design more effective mitigation strategies. Fortunately, urban heat islands can reduce through thoughtful planning and design. One of the most effective solutions is increasing vegetation coverage. The trees cool environments naturally while also improving air quality and comfort. Other effective strategies includes green roofs, green walls, reflective surfaces, permeable pavements, and shared public spaces. Heat island mitigation requires collaboration among architects, landscape architects, urban planners, and engineers. This demonstrates that environmental challenges often require interdisciplinary solutions. Water sensitive design represents a fundamental shift in how architects and planners think about water. Historically, urban development treated water as a problem. The goal was simple: move water away from buildings as quickly as possible. As a result, cities developed extensive drainage systems designed to rapidly channel water into rivers, estuaries, and oceans. While this approach reduced localized flooding, it often created larger environmental problems. These include downstream flooding, water pollution, groundwater depletion, ecosystem degradation, and increased infrastructure costs. Water sensitive design takes a different approach. Instead of treating water as waste, we recognize water as a valuable environmental resource. The objective becomes managing water intelligently within the site. Architects seek opportunities, capture rainfall, slow runoff, improve infiltration, recharge groundwater, and reuse water. This approach creates a more resilient communities. For tropical countries such as the Philippines, where heavy rainfall is common, water sensitive design is becoming increasingly important. Climate change is intensifying rainfall events, making traditional drainage approaches less effective. As architects, we must design developments that cooperate with natural hydrological systems rather than simply attempting to overpower them. Stormwater management refers to the control and management of rainwater after it falls onto a site. In natural landscapes, rainfall follows a relevant balance cycle. Water infiltrates into the soil. Plants absorb moisture. Groundwater systems are replenished. However, urbanization disrupts this natural process. When sites become covered with concrete, asphalt, buildings, and pavements, water can no longer infiltrate effectively. Instead, large volumes of runoff accumulate rapidly. This creates several problems. Flooding becomes more frequent, water pollution increases as runoff carries contaminants into rivers and waterways. Soil erosion becomes more severe. Stormwater management seeks to restore some of the natural hydrological functions that urbanization has removed. Strategies includes like retention ponds, detention basins, bioswales, rain gardens, and infiltration trenches. These systems slow water movement and allow natural environmental processes to function more effectively. For architects, stormwater management is no longer simply an engineering concern. It is an integral part of a sustainable site planning. One of the most effective water sensitive strategies is rainwater harvesting. Rainwater harvesting involves collecting and storing rainfall for future use. In tropical regions, this strategy is especially valuable because annual rainfall volumes are often substantial. Rather than allowing rainfall to become runoff, architects can compute water or capture water from roofs and other collection surfaces. The collected water can there be used for landscape irrigation, toilet flushing, building maintenance, emergency reserves, and non-potable uses. Rainwater harvesting provides multiple benefits. It reduces dependence on municipal water systems. It lowers utility costs. It improves resilience during water shortages. Historically, many traditional communities relied heavily on rainwater harvesting systems. Today, advances in storage technologies make these systems even more effective. As climate variability increases, decentralized water systems will likely become increasingly important in tropical architecture. Low impact development, commonly referred to as LID, is an approach that seeks to mimic natural environmental processes. Traditional development often transforms sites dramatically. Natural systems are removed, hydrological cycles are disrupted, ecological functions are degraded. LID seeks to minimize these impacts. The goal is not simply to develop a site. The goal is to develop a site while preserving environmental functions. LID strategies includes rain gardens, bioswales, green roofs, permeable pavements, and infiltration systems. These interventions helps maintain natural water cycles. They improve environmental performances while reducing infrastructure demands. Many contemporary sustainable developments now incorporate LID principles because they provide a long-term environmental economic benefits. For architects, LID represents a practical framework for balancing development with ecological responsibilities. Flooding is one of the most significant environmental challenges facing tropical regions. Historically, many communities attempted to eliminate flood risks entirely. However, contemporary planning recognizes that complete flooding prevention is often unrealistic. Instead, we focus on flood responsive planning. Flood responsive planning accepts that flooding may occur. The objective becomes minimizing damage and improving resilience. This requires understanding flood history, flood frequency, flood depth, and water movement patterns. Architects and planners then use this information guide development decisions. Strategies includes elevated structures, flood storage zones, adaptive landscapes, and resilient infrastructures. Flood responsive planning shifts the conversation from resistance to adaptation. This approach is increasingly important as climate change intensifies flooding events throughout tropical regions. Resilience has become one of the most important concepts in contemporary architecture and planning. A resilient community is not simply one that avoids disasters. A resilient community is one that can adapt, recover, and continue functioning. Flood resilience requires planning at multiple scales. Individual buildings must be resilient. Infrastructure must be resilient. Public spaces must be resilient. Community systems must also be resilient. Architects contribute significantly to resilience by designing environments capable of adapting to environmental uncertainty. As climate conditions become more unpredictable, resilience will become increasingly central to professional practice. One of the oldest and most effective responses to flooding in tropical region is elevation. Long before modern engineering existed, indigenous communities recognized that Floodwaters were an unavoidable environmental reality. Rather than fighting floods, they adapted to them. Traditional tropical architecture such as the Philippine Bahay Kubo demonstrates these principles clearly. The elevated floor system provides multiple environmental advantages. First, it protects occupants and property from floodwaters. Second, it improves ventilation beneath the structure. Third, it reduces moisture accumulation and improves durability. And fourth, it creates thermal separation from ground heat. Modern architecture continues to apply elevated design strategies, especially in flood prone areas. However, modern application often involves reinforced structure systems, elevated infrastructure, flood adapted utilities, and resilient community planning. As sea level rise and flood risks increase, elevated development will become an increasingly important design strategy. Architects must recognize that resilience often involves adaptation rather than resistance. Microclimatic modification is one of the most powerful tools available for architects. Rather than simply accepting existing environmental conditions, architects can significantly or strategically modify site conditions to improve comfort. This process involves influencing environmental variables such as temperature, air movement, solar exposure, humidity, and surface heat. For example, trees can reduce temperatures through shading. Water features can improve environmental quality. Building placement can direct airflow, and material selection can influence heat absorption. Microclimatic modification demonstrates that architecture is not passive. Architecture actively shapes environmental experience. The goal is not to change regional climate. The goal is to create a more comfortable localized conditions for the users. This concept becomes especially important in tropical environments where small environmental changes can significantly influence comfort. Creating cooler microclimates is one of the primary objectives of tropical site planning. The most comfortable outdoor environments rarely occur by accident. They are intentionally designed. Several environmental strategies contribute to cooler microclimates. The first is vegetation. Trees reduce solar exposure and cool surrounding air. The second is shade. Reducing direct sunlight dramatically improves thermal comfort. The third is airflow. Proper site planning allows breezes to move through spaces more effectively. The fourth is material selection. Permeable and reflective materials generally perform better than heat absorbing surfaces. These interventions may seem simple. However, when combined, they create significant improvements in environmental performance. Good tropical design is often the result of many small environmental decisions working together. Singapore is frequently recognized as one of the world's leading examples of tropical urban planning. Despite limited land resources and high population density, Singapore has successfully integrated environmental strategies in urban development. Several initiatives contribute to Singapore's success. These include urban greening programs, green building regulations, water sensitive planning, and heat island mitigation strategies. Singapore actively promotes vegetation throughout the city. green roofs, vertical gardens, urban forests, and public parks helps to moderate temperatures. City also invests heavily in stormwater management and water reuse systems. For architects, Singapore demonstrates that dense urban development and environmental sustainability are not mutually exclusive. With intelligent planning and strong policy frameworks, cities can become both highly urbanized and environmentally responsive. The Philippines offer many valuable examples of climate responsive site planning. Traditional settlements often evolved according to environmental realities. Communities adapted to flooding, monsoons, heat, and humidity. Examples include elevated dwellings, community clustering, shaded circulation networks, and landscape integrations. Modern developments can learn important lessons from these traditional approaches. Unfortunately, some contemporary developments ignores environmental conditions. This often results in flooding, heat accumulation, poor comfort, and environmental degradation. The challenge for future architects is combine traditional environmental wisdom with contemporary technologies and planning approaches. This balance represents the future of tropical architecture. Studying failures is often as valuable as successes. Many environmental problems originate from poor site planning decisions. Common mistakes include removing mature vegetation, ignoring natural drainage systems, overgrading sites, maximizing paved surfaces, disregarding environmental analysis. And these decisions often create long term problems that are expensive. Correct. Once a development is constructed, correcting site planning mistakes become difficult and costly. This is why environmental analysis must occur before design decisions are finalized. Good site planning prevents problems, poor site planning creates them. Now, let us summarize the major lessons from this module. First, architecture begins with the site. Second, microclimates strongly influences environmental performance. Third, vegetation functions as environmental infrastructure. Fourth, water sensitive design improves resilience and sustainability. Fifth, flood responsive planning is essential in tropical regions. And finally, architects possesses the ability to modify microclimates through intelligent environmental design. The success of a building often depends as much on site planning as it does on architectural form. As future architects, you must learn to view sites not as empty parcels of land, but as complex environmental systems. These questions are designed to encourage critical thinking. Architecture is not simply about creating buildings, it is about creating environments that support human well being. As architects, your responsibility extends beyond aesthetics. You must consider environmental systems, community resilience, sustainability, and long term performance. The topics discussed today form the foundation for environmentally responsible site planning. As we conclude our discussion on tropical site planning and microclimate, we now transition from the scale of the site to the scale of the building itself. Throughout this module, we learned how environmental conditions influences architecture before construction even begins. We explored site responsive design, vegetation integration, heat island mitigation, water sensitive planning, flood responsive development, and microclimatic modifications. These strategies helps architects create environmentally responsive sites. However, Even the most carefully planned site cannot perform effectively if the building envelope itself is poorly designed. This brings us to our next major topic: tropical building envelope and materials. The building envelope is often described as the skin of the building. It forms the boundary between the indoor environment and the outdoor environment. Every day, the building envelope must respond to solar radiation, heat transfer, rainfall, humidity, wind, and moisture intrusion. In tropical climates, these environmental forces are particularly intense. As architects, we must understand how roofs, walls, windows, insulation systems, and material perform under tropical conditions. One of the most important questions architects must answer is: how can we create building envelope that improves comfort while reducing energy consumption? To answer this question, we will examine several critical topics. First, we will study roof systems because roofs receive highest levels of solar exposure in tropical climates. They play a major role in thermal performance. Second, we will explore wall systems and insulation strategies. Although insulation is commonly associated with cold climates, it also plays a significant role in managing heat flow in tropical environments. Third, we will investigate moisture protection. High humidity and heavy rainfall makes moisture management one of the most important concerns in tropical construction. We'll see you on our next module.